you able to see the screen?
Yes.
Yeah. So, so this kind of does full overlap to what we have in class, what we had a discussion in the tech chat. And this diagram was shared with me in a previous course that I did, and I really like it and I use it to follow, to navigate myself through the business problem and what sort of direction I should be going in when looking at data preparation and modeling. So the first one here, the business problem is at the top because we need to understand what is our problem, what are we trying to achieve from our overall, what is our goal for any analysis or any predictive outcome. So we say, okay, well, if we're looking at only pure data analysis, we can come down this side. So we have the data analysis, and then we have a look at, okay, are we looking at geospatial, segmentation, aggregation, or is it just descriptive? So we can just do our data analysis if that's all we need to do and share that feedback. But then if we're looking at predictive outcomes, then we can start also asking ourselves, do we have enough data? Are we data rich? Yes, or are we data poor? Do we need to go and collect more information to be able to do our predictive outcome? If we're data poor, our probably best bet is to do some sort of A/B testing. But if we're data rich, we then have to say, okay, well, is our business problem, are we looking at a numerical, or are we looking at classification? And then if we're going classification, are we then binary or non-binary? And then some ideas straight below there are some what models we could use. So binary, the logistics, and the decision tree, and then we've got the non-binary, forest and boosted. Then if we've got facing our numeric business problem, then we can, are we looking at a continuous or are we looking at time-based? And then depending on what are we looking at, here are some suggested models that we can look at for either continuous or time-based. And then what Tom also mentioned as well, the only thing that's missing from here is the visualization along the way. Just visualize and tell that story as you're going.
Excellent. Thank you, Jonathan.
I have one comment. Okay, let's say this is a 3-page decision for how to solve a business problem. Okay, but sometimes, okay, it's great. It's really nice. I enjoy looking at it and how it's look like. Sometimes the decision, it's more overlapping and there is other also.
Yeah.
Yes, but in general, to start with this one, it's really nice. The most important overlap from my point of view, it is when your data is poor, how to enrich your data. Yes, I think here there is a lot of things to do, but it's nice. It's really helpful to look at it before to understand the overall, let's say, pipeline that we are looking for in general from business point of view. Thank you.
Yeah, it's very good. Kim, yeah, go.
Hey guys, good morning. So I have a question, Jonathan. Thank you very much for doing this. It looks really cool. When you say data poor, what was the reasoning behind why you chose to do A/B testing in particular? Like, why did you think that would make data more rich?
It's more of that you don't have enough data, and then when you're doing your testing, then that could be more clear to understand where are you missing that data. So if you've got all your data needed, it's a lot easier to do your numeric and classification. Whereas if you're missing a lot of data, your A/B testing is probably your better direction to go.
Then what are you testing for A/B testing? Like, I always think of A/B testing with marketing and like trying to make a decision one way or the other. So who would be the recipient of that A/B testing? Are you just taking a data set and then A/B testing a data set? I'm just confused about that.
All depends on your problem and how much data you have. This is just looking at a top down as a guide of where to go. It's not a concrete, but it's more of a guide on looking in where you should be going with your data, in which direction should you be looking at. And also you've got another example is if you're implementing a new web page, right? And if you want to get more, is the new web page going to be more beneficial to the company? Yes or no? But you don't have enough data of users, so then you create your test users and your non-test users, because you don't have the full information for those users that are possibly potentially going to access your web page. It could be, you could say, well, I'm going to have a 70-30% split of new users and existing users. I'm going to default them to one landing page, and the other people I'm going to default to another landing page. But then that's not a classification, yes or no. You're trying to understand, is the new landing page better for the business or not? Is it going to generate more revenue? Yes or no? Based on if my new landing page has a different layout. So there you would definitely use A/B testing, because you wouldn't have all the information of your users that are coming to your page. That's the best example I can share.
I want to explain a fun and that, well, it's not just an analogy, it's a reality. When you do A/B testing and you automate it, that is like a baby crawling version of reinforced learning. Because what you're doing, and I love, this is why I love beta distributions, you're doing there's different ways to do it, but you're kind of doing a running average. You're just starting with one of them. Let's say your company's trying 3 new landing pages plus the old one. Well, you can run them all, but carefully. So you start with the existing one, but every once in a while you randomly choose one of the new ones. And over time, it's this exploration component. It'll occasionally go try one of the new ones. And if one of those is significant enough, with that amount of exploration, it'll eventually be the winner and just start running that one most of the time. And then once you see which one has emerged as the winner, you turn it off and just use that one until you have a new update campaign. But I do have some code for that. If y'all remind me, I'll share it with you sometime. It's fun to code that stuff. It really is. But it has to do with the explore exploit of reinforced learning. It's also called Thompson sampling or one-armed bandit. There's too many names for all this stuff. All right. Well, as volleyball players would say, me go. I go. They have to use very quick sentences on the court. So I go. Let me share. Oh man, there we go. Wait a minute, I'm not trusting this. Hang on a second. I do that. Now if I do it. Sorry, I'm having there. That must be it. Okay, good. I think we're in good shape here. Y'all can see my notebook, correct? Expanding your faces. There we go. All right, feature conditioning, because I think we beat the you know what out of feature. Well, this is feature reduction, excuse me, but we beat the heck out of the feature conditioning, and I hope in a good way in y'all's minds. Okay, now why on feature reduction would I start out with linear regression and logistic regression too? Because it's a modeling algorithm and a primary tool. Okay, we use linear regression to study many things about a data set as we prepare it for use in predictive modeling. And I want to qualify this a bit. If we're in the realm of linear regression, logistic regression, neural networks, those are like branches, the big, when you see a big tree, you see the trunk and you follow one of the big branches, one of the big branches is linear and logistic regression, neural networks, deep learning, okay? But those more fancy things are really built on top of linear and logistic regression. The other big trunk of the tree is decision trees, random forests, etc., boost methods. As we just saw, depending on your data wealth, you might use that baby form of reinforced learning. But so many problems can be understood better and actually solved with very little data, or to get value with very little data in the linear regression realm. That's why we spend so much time on it, and it really does enhance your understanding. But we do hope to spend plenty of time on the tree methods. But we can use linear regression to help us even when we do not end up using it for our final predictive model in our ML pipeline. Now, have you all heard of the curse of dimensionality? It basically, we're a data-rich age. We get a lot of data, and any opportunity, even with neural networks, especially neural networks, that we have to reduce the dimensions of our data, not necessarily the amount of records, but the amount of features. So when I do this, we're talking number of features, right? When I do this, we're talking number of records. Well, it's nice to be rich in this direction, and it's nice to be adequate in this direction. Boy, how did we end up doing that with data? We kind of feel the same way about our physical attributes, don't we? Don't be fat, but be tall. Maybe not too tall. Okay. So thus, if we're going to use linear regression so much, it really is good to know the assumptions that it's based on. And if we have time, y'all saw that post I did debunking, hey, why was there ever an emphasis in any textbook about needing normally distributed data? Guys, I think I'm beginning to understand where it came from. It's not a requirement so much as it's a nicety if you want to do p-value analysis on the coefficients. I think that's where it came from, but I've not found any source to clearly state that's where it comes from. It's just based on my ongoing learning, my sleuthing on this topic. It seems like, oh, well, if you're going to do a hypothesis test to determine the significance of this feature, and that's related to the coefficient you get from linear regression, well, that hypothesis testing kind of does assume normally distributed feature data. But I would never turn down a data set because it had uniformly distributed feature data. That's great distribution, and you can still use p-values. It's just that you're going to upset some statisticians when you do that. And if you do, and you'd rather just quiet them than argue with them, you know, quantile transforming. So there you go. You can skew it and be dishonest for them. Okay, here are the assumptions. The model has linear relationships between features and labels. Now, we break this rule in the process of modeling all the time, but we're trying to unbreak it at the same, we're trying to glue it back together after, and you'll see what I mean. The model coefficients are linear. That is so confusing. It just means they're constant. By the way, there's realms of modeling where those coefficients are not constant. But thank God, we couldn't really solve those. No, we can't solve those without digital computing or Yugo, some other advanced computing that might happen in the future. Okay. the error term, now these are all related to the errors. The error term is linear. Now that's also not, that's kind of confusing. It just means, you remember I taught you all the envelopes for the error? When you see the shape, it means that envelope's not got variation, not significant variations in it. But also we want the error term to have a mean of 0. We're going to illustrate this with some fun modeling. All independent variables are uncorrelated with the error term. And we can test that visually and with Pearson's correlation coefficient. Observations of the error term are uncorrelated with each other. Ooh, what does that mean? That's kind of funky actually, but we'll even illustrate that. The error term has a constant variance. Okay, that's really, to me, I feel like these two statements are the same. I might be wrong as I continue to investigate more deeply because I'm not finding any sources to counter what I'm thinking. I will let you know. And then the error term is normally distributed. But even though this was the answer that Jim Frost came and gave to Dave Langer, who was backing up my post, even good old Jim Frost, the stats expert that's, supports data scientists, he was like, yeah, we just care that the error term is normally distributed, but even that's okay if it's not. It's just, I think uniform and normal distribution, they're both okay. And then of course, little or no collinearity. Now, as Yogita and I were discussing in Tech Time chat, can you use these modern solution methods like gradient descent and such, and fit a model with collinearity present? Yeah, you can. And you know what? It'll even be often more accurate than the model with no collinearity. I'm going to train y'all over and over and over. Do not get sucked in by the most accurate model. We'll talk about what model we most want. If Manjanatha were here, if David Lang, if Serge was here, our new author friend from PAC that Gaita and I made, he was backing me up on Harper's show yesterday. Preach it, Tom. Even Ben Taylor, yeah, well, that was some other topic. I was just glad because sometimes I go on a limb to say these things that I feel like no one else is saying, but they seem super important to me. Okay. When we create this fake data, here's our one fake feature. We're gonna test linear relationships between features and labels. What does that really mean? So here I've got some random feature data, and we're gonna pretend we don't know how we got Y, but this is how we're getting it. It's 2 times all the feature variables squared. And then we do a scatter plot, we get what we expect. And I'm leaving out noise for now, just to make this more clear. It wouldn't be a lot less clear with noise. It's just easier to visualize. Okay, now that I've got that, I want to fit it. Now remember, I'm flying blind. I don't know, well, I should have known right here, right? If I just do this visualization, the scatter plot, I know right away I'm going to need to engineer a feature, right? But I don't know for sure that it wouldn't be that it wouldn't be better to have x plus x squared and find the weights for each of those. But I start modeling and I just do a fit between x and y. And what do I find? Well, I get a prediction, but it's just doing its best because it's assuming a linear relationship. That's what's going on. And we could see right away, this is not a linear relationship. So the coefficient was 77. That's strange. It was only 2 on, now again, we're going back to profit mode. I know what the weight should be. Why? Because I created the model that created the fake data. Okay, we're trying to pretend we don't know so we can practice. But look, it got a model coefficient of this, and I didn't let it fit the intercept just for simplicity. But isn't that interesting? And so I think, all right, the linear regression algorithm assumed a linear relationship, like we said, and was able to fit a model that minimized the error, but it sure seems like we could do better. So let's try the feature engineering. And again, we already know from our fake data prophecy knowledge that it should be 2.0. So now I do some feature engineering and I do the part. Wow, now I have a linear relationship. This is all I really want y'all to see from this. This is a feature. Yeah, that's not linear. Well, yeah, it is. X squared is linear to Y. That's all we're trying to get. And if we have to do feature engineering to get there, that's okay. That's all I want you to take from this. And so we go back through all of it. Let's just look at this a little bit here. There is a linear relationship between X squared and Y. And it could be, again, there could be a case, like I said, where maybe we have 2 times X squared plus 10 times X. Well, we would investigate that because, again, we would have inherited that label and not known. Okay. And when we fit this model using X squared, we get exactly 2.0 because we don't have any noise. So there you go. Y actual versus and predicted, and the predicted is the line part, versus X squared, and then the R2, because I have no noise, that's the only reason this is happening. The R squared value, which is one of the metrics we'll learn, we haven't learned it yet, is 1.0. Just so you know, that is absolute perfection in modeling. Again, we have no fake noise yet. And we got the exact coefficient we knew we should get, as our fake data prophecy told us. All right. Now this is just text. All it's saying, guys, and I will add this to our course notebook that I've been giving y'all the link to. All this is saying is that M, this is the equation of a line, and we can make this multivariate. All the coefficients in your model have to be constant. That's all this means, linear model coefficients. But it goes, the reason it's talking about linear coefficients is because it relates to equations of the line. And the best way, if you wanted to derive least squares optimization from scratch using the calculus, you could do it. If you get stuck, go to my blog, look at the earliest post. I develop it in excruciating detail using different approaches, including linear algebra. And the linear algebra one is the one that hurts the most, but it's good. And I think Saul Kahn teaches it better than me. So you can go watch his videos on it too, because he does develop it with linear algebra also in both ways. He does it both ways. But this is all this means. And like I said, there are realms of modeling, especially in the physics realm, where usually these slopes in the physics realm represent system parameters. But if your system parameters have variables like a nonlinear spring, then you absolutely have to use digital math. Okay, now for the errors we were talking about. We assume homoscedastic errors. That just means you see this constant envelope that the errors fall within, roughly constant. That's all this means. Now, notice I was a good boy, wasn't a heretic, and I used the normal distribution to create the noise this time. So let's look at how I'm doing that. It's no big deal. I find the max of Y, and then this is the amount I want the noise to deviate from the mean. And so I go ahead and create a standard normal distribution of data, of noise, but I amplify it by what I calculated here. So that's all that's going on. And then, so that just gets added to Y by that method. And then of course, there's our error. So for that assumption, if I fit a regressor through it, look, it passes right through the middle. The methods ensure that we get a mean of 0, a mean error of 0, that is, and that we've got above and below the lines. Now, it's important to remember it's above and below this way, not this way, not at an angle vertically. That's thrown me off more than once, I'll confess. But if I now do a distribution of that error of y minus y predicted, so y predicted is the red, this is all the individual lines, yep, I get a normal distribution. And I'm not controlling the seed. So if you rerun this when I add it to our notebook, it'll do something, the distribution will look slightly different every time. If you notice that I'm only using 1,000 points, just for fun, if you push this up to 1,000,000, and I'm going to ask for a volunteer. Oh, thank you, Yogita. If I push this up to 1,000,000 points, what is this going to look more like? Oh, wow, it's still muted somehow. That's okay. I can read your lips. Yogita's saying, oh, Tom, you're challenging me on the central limit theorem. And as we get to a gobs of numbers, it'll look perfectly Gaussian. Great answer, Yogita. See, I could read her lips. Okay. Now, we've done this before, but I'm creating my fake data in a more reliable way. By the way, Dad makes mistakes. And Kaith and I had some embarrassing meetings over this. Well, more embarrassment for me than him. The fake data methods I was showing you earlier, they work great for classification problems, but they absolutely create strong collinearities among all the features otherwise. So this new method I'm using is easier and more reliable to not create collinearities. Again, creating fake data is not an easy skill, but it's a powerful skill. So how do we create heteroscedastic noise? That means it's not constant. It doesn't have a constant envelope. Well, okay, my loudest child, my eldest, is speaking in the background. Can y'all hear him very well? Okay, sounds good. So I'm using a small number of points just so it looks more clear. Well, maybe it doesn't look more clear, but I wanted to see some sparsity. So I create, I just do this over again for the number of points. And I'm going to compare homoscedastic noise to heteroscedastic noise. And you'll see how I'm using these fractions here in a minute. 1 second. So there's my Y max like I did before. Here's my basic noise for homoscedastic noise fraction. And there's where I create that homoscedastic noise. Here, to get the heteroscedastic noise, I need to create an equation for it. This is just a line equation to control that envelope like we've done in the past. And then I make YHS and what basic noise and hetero, I don't know why I said, I think heteroscedastic and basic noise, that's what those are for. So I plot the heteroscedastic noise separately, just so you can see what I'm adding to Y. And then I show the prediction is the blue line, the constant noise are the blue dots, and the heteroscedastic noise is the red dots. So even though we say we're only going to use linear regression for homoscedastic noise, we cheat all the time, guys. It's okay. These are assumptions. There would be nice to haves, but we break the rules to get work done. You just try not to. And so if there's some way to get rid of the heteroscedastic noise, you do, but it exists. And Yogita, I think you and I are going to have to deal with it on that California house price data set, right? FinTech, basic FinTech. Okay, now the next assumption, no correlation between independent variables and errors. Now, this isn't no correlation between features yet, although we are getting there. This is just between features and errors. Well, how can we do that? Let's just do a scatter plot between X and the errors. That's all you have to do. You can even run a Pearson's correlation calculation on this. But you would find, you're going to find that it's not perfectly zero, right? Because it's sample data. It's not the whole population. But that doesn't look very strongly correlated, does it? So I think we're safe. But you would probably find some small slope to fit this. Now, this is the one that's weird. Observations of errors are uncorrelated with each other. Now, I'm going to be honest with you. I'm guessing, and I think I'm right. But you would have to do a permutation of every possible equal set. In other words, I'm going to always have two sets, and I'm going to test a correlation. And so what are all the permutations you can have of each error point being in each set? All possibilities of that. Well, I only did one. I split it. This is the, if I indice the errors and I say, I'm going to take all the even ones. Now I want to show you this in case this is a wonderful NumPy trick. With NumPy, for each indice, for each dimension, you can do start, colon, stop. If you leave that blank, it assumes you're going all the way. And then step size. So all I'm doing is I'm getting all the even ones here in all the columns and all the odd ones here in all the columns. I'm just making two groups of the errors, and I'm making sure that if I do a scatter plot, there's no obvious correlation. Now, again, probably going to be some correlation value because it's not the whole population, but it's going to be very small. Okay, now this errors have constant variance. That's almost skedasticity. If y'all see it differently, let me know. I will keep investigating, but I don't know why. It almost seems like as I looked at all the various ways, I think these are saying the same thing. And then errors are normally distributed. We already saw that was the case up above, but it's also regarded as optional. Okay. Those are good things to go through when you're looking at a data set and you know you're going to use techniques of linear regression. You're going to use linear regression methods to help you reduce your feature set. Okay, so let's see where we're at. Good. And again, I will update the major notebook sometime today. Determine feature importance using plots of features versus labels. Okay, this is just basic scatter plot visualization of our features versus our label or labels. But let me show you what can happen. I'm going to go ahead and pre-create some fake data. I'm going to create my label, but I'm only going to allow this first time for the label to be influenced by one of the features. And I even have just a basic slope here. Okay, just one. And it's got noise. Well, that's strong correlation, isn't it? And we would expect that. We just visualize it. Yeah, we could fit this with linear regression. We could calculate Pearson's correlation R. But let's look at something interesting. When I change my label to be 1 times x1 plus 4 times x2, ooh, I can see that X1 is still important. I know it is, prophetically speaking, but if I were just to look at this, I might be tempted to think, well, I could throw that out. And thank God we know we shouldn't. This is enlightening here. But why does this one look so strongly correlated? Jonathan, can you help us out here? Why does this one look so much more strongly correlated than this one?
Why? Did you square it? I'm not sure if you squared it.
No, no, it's really just up here. Here we go into profit mode. 1 times X1. And again, this is NumPy-ish. It's doing it times all of X1 values, plus 4 times X2. Now, Jonathan,
because the
you're-
4.
You're one of my best students in my whole life. It's the 4. Yeah, I wasn't going to fault you for not being able to get, but it's the 4. It's just saying, look, it's being overpowered when I look at this versus this. So when you do look at these scatter plots, yeah, it's okay looking, but that doesn't mean this one's not important. It just means it's not as important. So if, and again, it's just the spirit of you. It's better to over visualize than under visualize, right? And so the spirit here is we don't want to trust this alone. That's key here. And because we're using a small number of points, even if we were to fit it, it looks like it would do something more like this. There would be a small slope to it, probably a slope of 1. Okay. In fact, going up to 150 from here is not unreasonable to suspect when I look at the weight of all this. And yeah, I could probably fit this separately and find, oh, that's 1. And then fit this data separately and find, oh, that's 4. So don't put too much stock in in your visual skills to see this. But let's look at yet another example. I'm going to go 1, it's implied because I don't have anything in front, 4 and 16 on the third one, and recreate my label with that. Oh, look at this now. It's just being overshadowed by the effects now of X3's 16. Oh, wow, even the 4 is not very obvious anymore. But the 16 is very obvious. So yes, we want to visualize when we're understanding things, but this still does give us an indication of feature strength. Just by doing this, I can find the feature that's most significant, can I? A quick scatter plots are easy. They're a dime a dozen. They're quick to run. And what's great about doing this, I can, in each of these cases, I found the most significant feature each time. And that's valuable. You can, this is report worthy. We have this label, we have this data. I'm still working. I just want to give you some immediate feedback. This feature is really important. You probably could use that to affect our business right now. So go do it. This is, guys, you're going to hear Geith and I emphasize this, and Greg too, by the way. If 80% or more of our work is before predictive modeling, do you think maybe 80% of the value we can give back to the organization is from stuff like this before we get to the predictive modeling? Yes, it most certainly is. And so you want to give a lot of early feedback on this kind of stuff. Okay, I'm wondering if I want to go into this yet, and I think I do. But it might be more fun. Forget the fun. Let's stick with the rigor. Okay. Now you might be thinking, wait, p-values. Don't use that to compare sample means to, claimed means of a population. And by the way, when you hear a population mean, don't ever trust that. That's just someone saying, we have a lot of data and we think we've approached the central limit theorem. But you can still find significance. You can reject the null hypothesis that we can't say there's anything different here. The reason we use p-values is this. The null hypothesis with modeling is that this feature has no correlation to the label. That would mean that you would get a coefficient of 0. But if you get a coefficient that is non-zero, well, there's a way to test that. But the test statistic equations and the methods of calculation are different than what we use when we're doing normal hypothesis testing, like one distribution to another. Because now, and this gets to that point of why I think statisticians care about saying, well, I want my feature distribution, the distribution of my feature values for this feature to be normally distributed. You know what I'm doing when I do this? Look at this, guys. What am I doing there? I'm figuring out which direction the wind's blowing. It's not very accurate, but it's good enough, you know? So if my feature values end up being more uniformly distributed than normally distributed, and a statistician is crying over that, I'm going to do this for him. And you know what that, I got to do this at the right end. You know what that is, guy? I maybe never showed you this Americanism. This is the world's smallest violin playing the world's saddest song. I would just tell my stats friend, hey, get over it. This is real world now. Okay, we're not that puristic, but I might eat my words later. I've done it before. I've said some stupid things even when I was teaching at the university level. So hopefully I'm not repeating, but I'm just saying, yeah, it would be nice to have, for this reason, for this analysis, it would be best if our feature variable values for a feature were uniformly distributed. I think we're okay still testing this with a uniformly distributed data. So to see what's going on here, I'm going to create some fake data again, create a fake label, add some noise to it. And I'm using a very small number of points because I'm going to force myself into using the t-distribution. And this gets to an important, you know that Geith and I love the history of math and science. And I want y'all to know what really drives the statistics world to push the boundaries to get accurate predictions. Why did the t-distribution, what is the metaphysical justification for the t-distribution? If we don't have a statistically significant amount of data, which is around 120 points, we can't really use the z-score and hypothesis testing with the normal distribution. We have to use the t-distribution. Now, forgive me for forgetting the name of the brilliant man that came up with the student distribute the t-test. But now we know what drives statisticians truly to generate their most cutting edge analyses. The taste of beer. Because this guy worked for Guinness and he had to work with small sample sizes, so someone that was testing it didn't go drunk, I guess. But anyway, we have the t-test, thank God. And the main difference is, let's say this is the normal distribution. Now I'm going to hyper-emphasize that. See where my finger's in it? For a small, let's say 10 samples, the t-distribution would just have much wider tails. Check it. Well, here, I've got it open. Wikipedia. Let me see if I can find it. There we go. I'll show you. This is fun to look at. Let's bring it over. So you can see these, here is a degree of freedom of 1. That means there was only 2 samples, and yet we can still get some value from that. There's the distribution for that. You see it having the widest tails out here. And then as the degrees of freedom, meaning the number of samples minus 1, approach affinity, the t-distribution approaches the normal distribution. All right. So, but as we get like 100, 120, you can go back to the normal distribution, no problem. And frankly, if you use the scikit-learn tools and the SciPy tools, do you even have to worry about that? No, it's going to do it for you. And I haven't dug into the code that the scikit-learn authors wrote for that. My guess is that they probably just stuck with the t-distribution, because if it approaches the normal distribution and really the calculation expense of it's not a lot worse, well, you'll see it is a little worse. So I go on ahead and do a fit. Again, you see, we're being data centric here. We haven't really done anything to cover this. Okay, is it just me, or do y'all get really frustrated with the mouse work in these cells? Sorry, I'm going to whine a minute. It really bugs me. We're being data centric in this course, even though we have talked, but please, if you want to get into the math of how you do linear regression, I go into painful detail in my earliest blog posts on this. Then we do the fit. We're going to predict, this time we're going to we haven't been using the intercept. We're going to do it. We're going to keep a copy of X. And so we get our intercept and our coefficient, and look what we got. This is pretty good for small amount of data with noise. We got close to our prophecy values, didn't we? We know it should be 1 and 0, but hey, that's not bad for someone that's flying blind. Well, let's look at these calculations that I told you about. Here's what we'd have normally done. Normally, these would have been the difference between eldest, thank you. My oldest son is so loud. Wonder where he gets it from. Okay, so here's the assumption that this is the alternative hypothesis, that no, there is a significant coefficient. And here's the assumption that no, there's no correlation of this feature to the label. And we're doing this, but we need to divide this by some type of error term, like a standard deviation, but we need a special one for when we're doing this with linear regression. So we've got, Gabe, please. Oh, Luke, that was Luke. Where CJ is, okay, so basically these are the original Y values minus each of the predicted Y values. And you square those differences and sum them up. And you divide all of those by the number of samples minus 2. Then in the denominator, you sum up all the X's minus the mean of the X and square, you sum those squares. Now, the t-distribution is this. And the gamma function is its own thing. This is one version of it. But I'm finding, I'm still developing this, but it's coming good. But there's another version that uses the beta distribution, and I'm going to use that. But if you don't have to do this math, it's done in the modules for you. But as you know, I like to code from scratch, compare. I was getting pretty close with the gamma, but the way I was doing the gamma was a bit sketchy. But we're gonna bypass what I was predicting, which you can see it was getting pretty close. Got the standard error exactly with the modules, but my p-value is still a little off, and I think I know why. But if we just use the stats libraries, it gives us all this great data here, and among them is the p-value. Now, if you're still learning about p-value, I sympathize, it can be hard, but is this telling us that we can reject our null hypothesis that there's no correlation between feature and label? What do y'all think? Just raise your hand if you want. What do you think? This is saying that, hey, this is significant, meaning you're not falling in within the realms of possibility that the null hypothesis is true. You're way outside, you're way out on the tails. There's no way that the null hypothesis is true. There's definitely a link between this feature and your label. That's all this means. And here's another way to go about it. And I just haven't, there's another way to present these parameters. Let's see if I can, well, this creates a really rich thing. And I will have,
Sorry, Tom, doesn't it show a report when you use the stats?
Yes, in fact, Jonathan, that's what I was worried about. Let's do it this way. I'll just have to run the whole notebook, but I think we'll be fine. It should run without errors based on what I've been doing. Well, we may not have to run the whole thing. I don't think we'll have to run the whole thing.
Yeah.
Let's do it this way. So I think I only need to come up to here. We should be good. In fact, I don't even need to run my cells. I'm going to go without my cells and just don't need that either. So here we go. Oh, it's going to croak because I need to run some of the stuff above. Here we go. I still need to run this. Okay, we should be good from here. I wanted to, yeah, I wish that I had just left that. I was experimenting, Jonathan. I wanted to record it better, but yeah, let's show them this, what you and I are talking about. Okay, so this is kind of cryptic, right? But this is super rich. The only thing I don't like about it, this is so awesome. Gives you the R squared. You can see we're doing great. R squared adjusted, the F statistic, and we'll go over that next week, hopefully. But you can see it's reporting our, and it re-randomized, so everything became a little different than I showed you before. But here's that standard error I was showing you all how to calculate. Here's the t-test for the, this is the intercept when it says constant. And for x1, here are our p-values. And look at that. It's saying, hey, this isn't important. Now, I'm not buying that. You don't need this. You don't need this intercept, and that would be great. Here's our confidence interval. And so we'll talk about more of those next week. But notice you can get the parameters, the model parameters, or you can get the whole summary. I was trying, Jonathan, all I was doing was experimenting. How can I report individual things? And I'm still not there yet. But it's been a long time since I used this one, but I remember I loved this report. Hey, we're at a good stopping point. Sorry, we went a little over, but again, never hesitate to say, Dad, get those up to the notebook. I will try to remember.